Let's examine the property of time shift. We have a signal x of t and it will be delayed by t naught. In addition to that, we also is going to delay the unit step by t naught. So this function then looks like this. So for example, here is t naught, and there is nothing in between, or there's no signal before t naught due to ut minus t naught. Now, so what does the Laplace transform of this signal looks like? It is xs e minus t naught. Let's prove. So the function that we want to find the Laplace transform of is this. We put this function here and we integrate this function from 0. So we are looking at causal signal to e minus st dt. Now, we set tau equals to t minus t naught. So this becomes tau. This becomes tau. So this is t equals to 0. Therefore, t equals to tau minus t naught. Oh, tau plus t naught. So tau is equals to t minus t naught, but t on the lower position of the integral is 0. So therefore tau is equals to minus t naught. Well, t equals to infinity, so tau is still infinity, minus t naught, so it's infinity. Now dt becomes d tau. What about here? So t is equals to tau plus t naught. So that's why we've changed the integration over here. Now we can then open up this to become e minus s tau times e minus s t naught. We can bring this expression outside, and so this therefore looks like our typical Laplace transform equation, which is x of s times e minus st naught. So in conclusion, the Laplace transform of the time delayed signal is xs times e minus st naught, where t naught is the value that is time delayed. Let us see the use of this time shift in an example. We are given xs. Now remember that anytime when we can see e minus st naught, this gives us a hint that the signal is being delayed, and in this case it will be by 2 seconds. So how do we take this complicated expression and break it up? Again, we use partial fraction expansion, and we have s plus 2 on the left hand side, and we'll collect only one of the expression, which is s plus 3, and the other expression 5e minus 2s, we'll do it here. Now we then perform again, well, I guess this is not partial fraction expansion, this is just to what do you call that, to simplify the expression and bring the numerator into this form. Now by partial fraction expansion, we are going to solve for the first term, we call it x1, and the second term we call it x2, and you have to learn how to do partial fraction expansion. The idea is this expression on the right is the same as the expression on the left. Now you can check by your collapsing the terms together, as well as here, expression on the right is equals to expression on the left. However, notice that expression on the left is 5e minus 2s, but here we're only dealing with 5, because later on you'll realize that we are interested to exploit the e minus 2s term. How do we do that? Well, the x2s will have this term, x2s e minus 2s. The x1s is this guy. So let's study the second term. x2s e minus 2s, when we perform inverse Laplace transform, 5 over s plus 1 becomes 5 e minus 1t by lookup table. 5 over s plus 2 becomes 5e minus 2t in the lookup table. So we have 5e minus t minus 5e minus 2t ut. What about the e minus 2s? You will introduce the time delay here. So you have e minus 2, t minus 2, and as well as 5e minus t becomes 5e minus t minus 2. Additionally is ut minus 2. So remember, this is the property that we are using. A time delayed version will have a xs multiplied by e minus t naught. We are using this in this expression over here to get this expression on the bottom, which is a delayed version t minus 2. x1 is the standard one, so you can get the results easily by inspection. Lastly, when we have x of t, that is Laplace transform into x of s, if we multiply x of t by a complex exponential e s naught t, then the Laplace transform, the s is replaced by s minus s naught. So in our example, we have a cosine bt ut, which is we have the right hand side, which is s over s squared plus b squared. When we introduce e minus at multiplying by the expression, then what happens is that all the s will become s minus a. Which implies that it will be replaced by s plus a. So you see that all the s will be replaced by s plus a over here. The proof is in this one line equation. Simply, if we insert xt times es naught t, and we can now bring the exponent of this exponential together. So what we find is that we are now integrating xt with respect to e minus s naught t. So therefore, x of s minus s naught is the result. Okay, before I leave, there's some examples which you can, there are references where we can find these properties, as well as examples of derivative and integral, and using Laplace transform to solve differential equation in Trevor Bersad's YouTube video, which is useful. Thank you.